Hi everyone, in this lesson we are going to introduce chapter 7. We are going to look at the concept of Cartesian vectors. Now in chapter 6 we looked at geometric vectors. So we're going to move on to Cartesian vectors now, and the main difference is Cartesian vectors are vectors that are graphed on a 2D plane, an xy axis. Now a Cartesian vector, to define a bit more exactly, is where the endpoints can be defined using Cartesian coordinates. If a Cartesian vector has its tail at the origin, it's called a position vector. So this vector v right here, it's a position vector. And we also have another vector u right here. Now, the position vector can be defined by square brackets. So what we have is, we basically have vector v is 2 and 1. 2 here is just represents the change in the x-axis, right? If it's going 2 units to the left, and the 1 here is the change in the y-axis, and goes 1 unit up. Now, what do you notice about vector u? It has the exact same change in the x value and the change in the y value as vector v. So vector u also has the same magnitude and direction. It goes 2 units to the right and 1 unit up. So it can also be referred to as 2 and 1. So the two vectors are basically equivalent vectors. Now, we can also define Cartesian vectors in terms of unit vectors. A unit vector is a vector with a magnitude of 1. In this case, we're using the unit vectors I and j, and vector I, the unit vector, is just a change in the x value, and unit j is the change in the y value. So we can just write vector u and vector v as, in this case, 2i plus j, right? Because we're getting we're moving 2 units to the right and 1 unit up. All right, let's look at the magnitude of a Cartesian vector now. The magnitude of a Cartesian vector is found using the same formula as the distance of a line segment, right? So just think of the magnitude as the length of the vector. And if you guys remember the formula for the distance of a line segment is basically just found using the Pythagorean theorem, right? Okay, so remember, u1 in this case would represent the change in the x value, u2 represents a change in the y value. So just like how the distance between 2 points in the line, or the distance of a line segment on the Cartesian plane, is found by, if you remember, the distance of 2 points on the Cartesian plane is x2 minus x1 squared plus y2 minus y1 squared, right? Like if we had 2 points on a Cartesian plane, let's call this x1, y1, and this would be x2, y2. Whether it's 2 points or the distance of a line segment, they're the same thing, right? The difference between the two, all right, the difference between the x values is the horizontal distance, right? And the distance between the y values is the difference between y values is the vertical distance. So if we squared those and got the square root, if we squared those, add them up, and then got the square root, then we would get the distance of this line segment right here. And the same reasoning applies for the magnitude of a Cartesian vector. So we just square u1, which is the change in the x value, and we square u2, the change in the y value, add them up, and then get the square root of it, that sum. All right, so let's look at example 1. Let's find the magnitude of this vector u right here. First off, we have to define the Cartesian vector. We see that we go from 1 to 13 on the x-axis, right? We have a horizontal displacement of 12, and we go from 2 to 7 on the y-axis. So we have a horizontal displacement of 5. So we just have to plug numbers into the formula, right? The magnitude of vector u will therefore just be the square root of 12 squared plus 5 squared. That's 169, and the square root of 169 is 13. Next up, adding and subtracting vectors. It's much easier to add and subtract vectors that are represented as Cartesian vectors. All we have to do is add and subtract the unit vectors. So we add and subtract the change in x, and we add and subtract the change in y, depending on whether we're adding or subtracting. All right. So for vector u and vector v here, we just add. If we're adding the vectors, we just add the change in x values, and we add the change in y values. If we're subtracting the two vectors, we subtract the change in y values, and we subtract the change in x values, and then we subtract the change in the y values. All right, let's look at example 2 now. We got two vectors right here. We can try adding them and subtracting them. So if we were to add the two vectors, all we do is just add the x values. So 3 plus 5, and then 6 plus -2. That should give me 8 and 4. If we were to subtract the two vectors, we would have so 3 minus 5 and 6 minus -2. That would give me -2 and 8. All right, next up, multiplying Cartesian vectors by a scalar. And so in this case, when we multiply a Cartesian vector by a scalar, we just multiply the unit vectors by the scalar. So the change in x and the change in y, we just multiply it by the scalar, and that'll give us the resultant. Right? So if we add number k multiplied by the vector u, we just distribute the k times u1 and k times u2. All right, let's try example 3 now for the vectors in example 2. All right, let's try getting 3u and then 3u minus 2v. So 3u will be 3 times 5 and -2. All right, and so just distribute, right? 3 times 5 is 15. 3 times -2 is -6. For b, okay, we got 3u minus 2v. So that's 3 times 5 minus 2 times 3 and 6. And we already established what 3u was in A. So 15 and -6 minus, we can distribute this here, 2 times 3 and 2 times 6. Right? So this would be 15 and -6 minus 6 and 12. So we're going to get 15 minus 6 and -6 minus 12, which will give me 9 and -18. Next part, expressing a vector in Cartesian form with the magnitude and bearing. So if we have the magnitude and the bearing of any vector, we can convert that to Cartesian form by using sine and cosine. Now, if this looks familiar, this is exactly what we did in 6.5. So 6.5 was just a preview of this. We're converting a vector of magnitude and bearing to the vertical and horizontal components is basically converting it to a Cartesian vector. So let's look at this example. Vector v has a magnitude of 6 and a bearing of 40 degrees from the horizontal. So this right here should be 40 degrees. Write the vector in Cartesian form. So you can just think of it this way, right? We basically have like a right angle triangle here, right? Okay, so we can use sine and cosine to determine the change in x and the change in y. Cosine for the horizontal component, right? So that'll give us the change in x. So 6 cosine 40 is approximately equal to 4.60. 6 sine 40 will give us the vertical component. That's 3.86. So we can express this vector as 4.6 and 3.86. If you want to write it as a sum of unit vectors, I can write it like this as well. 4.6i plus 3.86j, like so. Maybe we should label it as well. So that pretty much concludes today's lesson. We covered quite a few small things, but nothing too challenging. It's basically our introduction to Cartesian vectors. Here are the practice questions that are also in the notes. Please complete them and check your answers, and then try doing the assigned textbook questions.